Thank you for joining this mini webinar, mini conference. And it is my pleasure to introduce to you the speakers of today. So our first speaker will be Martijn Anthonissen from Eindhoven University of Technology, the Computational Illumination Optics group. His research focuses particularly on non-imaging freeform optics, imaging optics, and improved direct methods. Particularly focusing to the development of inverse methods to directly compute the required optical system, with the ultimate goal to develop advanced simulation tools that can be used for virtual prototyping. So during this webinar today, he will give a presentation on the models using optimal mass transport for inverse design in non-imaging optical systems. Martijn, can I ask you to share your screen?
Yes. Let me check. Okay. Can you see my screen now?
Yes, perfectly. Thank you. So the floor is yours.
Thank you very much. And I would like to thank the organizers for the invitation to speak here today, which is a great pleasure. So as Lien just said, I will be talking about models using optimal transport for inverse design. And in one slide, this is the problem we are solving. So you know the original story about the frog who turns into a prince after being kissed by a princess. Apparently, I found on Wikipedia that in the original versions, the frog was thrown against the wall. We're going to do it a little bit differently today. So the idea is we have a light source located here. It sends out a parallel beam going up. And the light distribution at the source is this frog pattern. And our goal is to have the prince here on the target screen. So the question is, can we compute the shape of this mirror here? So the mirror has a free-form surface. Can we compute it in such a way that indeed the frog turns into a prince? And this is a problem that has been solved by Lotte Romein, and she was a PhD student in our group and defended her PhD thesis in 2021. She now works at Signify Research in Eindhoven in the Netherlands. And a brief outline of my presentation, a little bit about the work we do at the Technical University of Eindhoven, then on non-imaging freeform optics, and I want to present a mathematical model for 16 basic systems. I will also show you how we solve them numerically, and then I will show some results, and I will also go beyond these 16 systems. So just a quick overview of the group. At the top line here, you see the staff members. So with me, that's Wilbert IJzerman, who works at Signify Research and is a full-time professor 1 day per week at Eindhoven University. My colleagues Lisa and Koen, the assistant professors, they joined about 2 years ago, and Jan Tentij Boonkamp, associate professor. Then below that is the list of our current PhD students, and the bottom 2 rows are the PhD students who have already graduated at TUE. And what we work on, we have 4 research lines. So one, and that's mostly what I will be talking about today, is inverse design in non-imaging optics. So non-imaging optics, think of street lights, car headlights, etc., and luminaires that you have at home. What we aim for is to directly compute the optical surfaces that turn a given source into a desired target. The mathematical disciplines that we use there are optimal transport, solving nonlinear partial differential equations of Monge Ampère type. Then more recently, we also started working on inverse design in imaging optics. So think cameras, telescopes, and so on, where the goal is you have some object and you want to have a very precise image without aberrations, without deviations from a linear transformation. And the mathematics we use there is Lie algebra to describe these aberrations. You can find analytical expressions for aberrations. And if you have those, you can aim to make them as small as possible. We recently got granted a research proposal on AI for optics, so artificial intelligence methods for optical design. And here we want to use AI methods to design new optical systems, both in imaging and non-imaging, which are flexible to handle different constraints, uncertainties, and even generative AI to look for very problem-specific optimizers. And finally, in many inverse methods. You will also need fast simulation methods, fast direct methods. And there we have been working on ray tracing in phase space and also using Liouville's equation, which is basically computing a partial differential equation, solving it numerically for an energy distribution in phase space. And it's an alternative to ray tracing. Today, I will be talking about non-imaging freeform optics. So in the picture on the right, you see a road, and on the one hand, you have the street lighting. You would like to have a nice uniform light distribution on the street. You do not want to send light into space. If you think of an urban environment, you don't want to send light into people's houses. So which shape should the mirrors or lenses have that are in these street lights to accomplish that? You also see the car headlights in this picture. I will not talk about that, but that would be another example. The traditional state-of-the-art method is to come up with some design, do ray tracing, and then see if the performance of the optical system is what you want. If not, change it, do ray tracing again, and so come with an optical design. What we aim to do is directly compute the optical surface, lens, mirror that accomplishes this. And for that, I will show you in a bit that we need to solve a partial differential equation. So what we have developed in time is one mathematical model that can solve these 16 basic systems. So what you see here, the top 8 systems are reflector systems. The bottom 8 are lens systems, and these are 2D cartoons to illustrate what we aim to do. So either we have a parallel beam of light, a parallel source, or a point source. And for targets, we have also a parallel beam or a point, or a screen close to the optical system, a near field target, or when we just look far away from the optical system and basically we're interested in how much light is sent in which direction, we have a far field target. You see here mirror systems, lens systems that accomplish this. And for the lenses, if you see here a bold, a thick lens surface, it's a freeform surface that we compute. This lens surface here is thin. It's a straight line here. It doesn't influence the light rays. So I will briefly talk about 3 systems indicated in yellow here. And I will show you how we do the mathematical modeling. Of course, we solve the problem in 3 spatial dimensions, but that leads to very complicated equations. So to make it clear, I'll first move to a 2D problem. So here you see a light source and here light rays. And with the light rays, I try to indicate that we have much light in the middle and fewer light at the edges. So the light distribution here is like a Gaussian. And I want to compute these 2 reflector shapes in such a way that at my target here, I have a nice uniform distribution. So if you look at the energy distribution here, you see it's flat, it's constant. And there is a mapping that tells if you pick a coordinate in the source where a light ray starts, it will end in the target at coordinate y. So this is the optical mapping that tells starting and landing position of a light ray. What you also already see in this picture is that the area under the graph on the left should be equal to the area on the right, which means that no light is lost and no light is created in the optical system. So this is conservation of energy in a sense. The way we model this is that we introduce some coordinates, so x and y for the source and target coordinates. The z-axis, the optical axis, a light ray leaves here at the point P, hits the first reflector, and z is u of x is the description of the first reflector, so the shape. So u is an unknown function that I'm trying to find, trying to compute. The light ray hits the second reflector at B, and B I describe in this way. So it's capital L, the distance between source and target, minus w of y, and y is the coordinate in the target. This w is the second unknown function I'm looking for. So I'm trying to find u and w, and then I have the shapes of the first and second reflectors. We look at the optical path length. So a light ray travels the distance u from source to first reflector, the distance between the 2 points where the reflectors are hit, and then w from the second reflector to the target. With the coordinates, you can find d here, and you can rewrite this in such a way. So what I have here on the left are my 2 unknown functions u and w, and apparently the sum equals sum cost function, c of x and y. So this expression here, in principle, this is known. So capital V and capital L are constants that I choose in designing my optical system. And then I have, in principle, a known function here. This formulation is known in mathematics as an optimal transport formulation. And in principle, this is the same problem as when you have a pile of sand on the beach. You would like to build a sandcastle. You use all the sand, you transport it from the pile to the castle, and then the C is actual transportation costs that you would like to minimize. There are many solutions here, and we often pick a special pair. So we pick U as the maximum where we maximize over Y C minus W, and for W the other maximum. The reason we pick these types of solutions is first to render it unique, second to have nice convex or concave surfaces. So what you see here from the second equation, since we have a maximum, if I differentiate to x, I should find 0. And if you take now the cost function from the previous slide, and indeed you compute the derivative to x, and then you look at this equation here, then you can already find the optical mapping. So the optical mapping is this function here. There is one thing I didn't use yet, which is energy conservation. So here what you see is I have a source light distribution F, target light distribution G. In my figure, S is here from -1 to 1. T is from 3 to 4. And now if I integrate in the source from -1, the left side, to some point x here in this interval, I would like it to be the same as where I end up at the target. So the target here in y, from the optical mapping of -1, which can be either the left point in the top graph or the right point in the bottom graph. So you see here the light ray goes from this point all the way to the right and ends at the right. And then I should pick a minus sign here. And if I replace y with the optical mapping, I get this m prime from the coordinate transformation. And since this should hold for any x, I now find an ordinary differential equation for m. And this ODE, that's a standard thing in mathematics. There are many numerical routines for that. You can easily solve that, which gives you the optical mapping. And then I go back to my optimal transport formulation. U plus W is C. I substitute mx. And now I have an ordinary differential equation for U. If I solve that, I have found the shape of the first reflector. And then finally, I have this relation here, still U plus W is C. I replaced Y with mx, and this gives you the shape, in an indirect way, of the second reflector. And indeed, if you solve that numerically, you find the two pictures on this slide here. So two different solutions that both do the task we wanted to do. So here are the equations in the 2D case where I added one thing. I wrote this expression here as phi prime. So phi itself is basically the antiderivative of what it says here. So I have x squared plus v minus L times u. And then the energy conservation, I can also express that as the second derivative of phi equals f over g. Now, if I go to 3D, which is of course the interesting case, then my x coordinates will have two components. Similarly, my y in the target also has two components, and my optical mapping has two components, also m1 and m2, two functions. If you would do the derivation of the model, you would find an optical mapping that is very similar. So it's x plus v minus L. Here I had a first derivative. Here I get the gradient of u. So two first derivatives. And then I can also write that as the gradient of some function phi. The optimal transport formulation, again, very similar. Here I have y minus x squared. Here it's the distance between those 2 points squared. Energy conservation, this m prime came from a coordinate transformation. If you do it in 3D, you would get the determinant of the Jacobian matrix. So this here is the matrix with the first derivatives of m. If you write that in terms of the function phi, you get this partial differential equation. So this derivative of phi equals f over g, the energy distributions that you know. So you see this nonlinear because here I have a product and here is a square. And this is called the Monge equation. So it's a second order nonlinear partial differential equation. Now, another system parallel to point, what you see here is the source is the same, but now we have a point target, and now I would like the energy in my example to be uniform in the angle here. So again, problem is the same, find the shapes of the reflectors. The modeling is similar. It's a bit different because now here at the source, at the target, we have one point, but we look at the direction here. And I can get to a very similar formulation by rewriting. I find the equation we have here. And if I take logarithms now, I find again an optimal transport formulation. What you see here is that my cost function now becomes the logarithm of what it says here. So it's a non-quadratic function, which is more complicated. We also have energy conservation here. That's very similar to what I did in the previous example. So I'll quickly click through. Again, two solutions, one with crossing rays, one with non-crossing rays. This is the 2D formulation. In 3D, what we get is energy conservation is again in terms of the determinant of the Jacobian matrix. We have the optimal transport formulation, very similar between the 1D and 2D example, or 2D and 3D if you like. And then to solve it, what we do is we look at this formulation here, we differentiate to X, substitute the optical mapping, differentiate again. This matrix here I call C, this one I call P, and then we have a generalization of the Monge-Ampère equation. One more example. If I look at the parallel to near field lens example, so here is the source, here is the target, and now I want to find the shape of this lens surface here. The bottom one is straight, so it doesn't influence how the light rays travel. If you model this, and here I extended the lens because, well, the bit of air here is not important. But what you now get is that you see here is an unknown function that depends on the y target coordinates. In here is the unknown function u that depends on the source coordinates. And here I cannot separate them. Here they're really mixed in a complicated way. I cannot find an optimal transport formulation here. But what you could do is if you look at this relation, so here's energy conservation again, same as before, we had this relation, but now if I differentiate this to x, you see that the v drops out, this unknown. So if I differentiate this relation to x, I get an ordinary differential equation for u, and then I can compute the shape of this surface. And you see again, we find one for the plus, one for the minus sign with non-crossing or crossing light rays. So what we have done so far is here the 2D formulation, here the 3D formulation, and it gets a bit more complicated again. So now I have this equation here, I differentiate to x, the v drops out, I only have the unknown u in here. This is just a little bit of notation. I can substitute the optical mapping and differentiate again. And now I find an equation of this type. So what you see here is again a generalization, and this is called a generated Jacobian equation. To summarize what we have seen, all of these 16 systems can be described either with the standard Monge-Ampère equation, generalized Monge-Ampère equation, of one of these generated Jacobian equations. The circles that you see on the left, one circle is standard Monge-Ampère, two circles, like in this example, is generalized, and you see all the near field examples are 3 circles and they're all generated Jacobi equations. The mathematical model is very similar. I can always write it in this way. Equation, the C and P depend on the model. And we have written that in this paper in Optics Express, and also Lotte's PhD thesis is a very nice overview of how this all works. Now, to solve it numerically, we need also in 3D a boundary condition, which is here the transport boundary condition. So it tells that the optical mapping, light rays that leave at the source, the boundary of the source go to the boundary of the target. We break it down in steps, so we solve it numerically by finding a P and then a mapping from boundary to boundary. And we do that, this is going very quickly, but we have written a number of papers on this. We minimize this functional to find a new approximation for the P matrix. Then we make sure that the boundary fits or gets better, and then we update the mapping. So you see that this is an iterative scheme that computes the optical mapping that performs what we would like it to do. Let me present a few examples. So one here is laser beam shaping. So on the left, we have a Gaussian profile, parallel beam of light, and we want to compute the two lens surfaces in such a way that we get a top hat target. This was done by Nitin Yadav, and you see here the lens that he found with crossing rays. This is the desired target distribution, and this is what's being achieved, checked using ray tracing. So that's why you get this little spiky behavior, because we use ray tracing to verify that indeed we found the correct solution. Here you also see that there are alternative optical systems. So this is the one from the previous slide. This is the one with non-crossing rays. And this is a transform from air to glass to air. But of course, you could also assume that the source is in glass. So that's what you see here. And then we have air, and that the target is again in glass. So that gives two alternative solutions. Another example by Teun van Roosmalen, he worked on the point-to-parallel reflector system. So you have a point source, and here all the axes are free. And he computed the two reflectors that are needed to have a parallel beam and also do, of course, the energy transformation from from a given energy distribution in the source to a desired one in the target. And another example by Lotte. So she has a parallel beam of light here leaving from this plane going up. It's being reflected by the mirror that you see back to the plane z equals 0. And there it forms the logo of the Society for Industrial and Applied Mathematics. And then to show an extension here, this is one of our current PhD students, Peter Braam. And what he has done is take a uniform source and computed two reflectors in such a way that if you would put a target screen at this position here, that you get a light distribution that has the shape of an egg. And if you move the screen to this position, then you get a light distribution that has the form of a chick. And if you go in between, that's what you see in this slide. The blue screen that you see going up and down, that shows on the right the landing positions of light rays that leave from a uniform grid at the source. And then the landing positions you see, they indicate the energy distribution, and at the very top it has the shape of a chick. And if you go back to the first position of the target screen, you see that it has the shape of an egg. So the mirrors are fixed, but depending on where you put your screen, you get a different energy distribution. The reason we look at this, it seems very academic, is that we would like to incorporate, this is all geometrical optics, some of the wave characteristics. Because we know the distance and optical path length between these two screens, we can extract some phase information. So that's one of the reasons that we look at this example here. So to conclude my presentation, what we have seen is mathematical models for freeform optical design. We have one mathematical framework for 16 basic systems, and we have also seen that you can do extensions there. We have developed a least square solver that directly computes the freeform optical surfaces required. And we've already seen the extension of the parallel source to two illuminance patterns. In future, we will be working on using artificial intelligence, so generative AI for optical design. We are also currently looking at finite sources, so not a point source or a parallel beam, but also, for instance, an interval in 2D that sends out light every point in multiple directions. We are also very interested in gradient index optics, computing what the refractive index should look like, and to include phase information. You can find more information on our group's website, and the link is on the slide here. And if you know of any master students that will be graduating soon, we have a number of open PhD positions. So we still have multiple PhD positions open. And if you know of anyone who would be interested, feel free to give them my details so that they can contact me. So that concludes my presentation. Thank you.
Thank you, Martijn, for this presentation. If there are any questions, please put them in the chat. I received already a question from Lun Yang. You indicate energy conservation. That's basically what is also called or referred to as étendue conservation. The classical way of energy étendue conservation is calculated based on integration over a surface. But in non-imaging optics, we use contour integration to simplify it, only integrate over the boundaries. Does this play a part in this energy conservation calculation? And could contour integration potentially help?
I'm not sure about contour integration. It is not entirely the same as étendue conservation here, because this is all zero étendue, right? I use zero étendue sources. It's ideal sources, either a point source or a parallel beam of light, which has zero area and phase space. So you could also have like an area in phase space and then preserve that. But it's different things here.
Okay. Perhaps a question from my side following on this. So if you want to test this in a lab, you will use a real source. Of course, you can first start working with an idealized source where you collimate your source and so on. But given the model, do you see any chance or difficulties to implement real source characteristics?
Difficulties are plenty, but we are working on that. So we also have inverse methods. We are developing them currently for finite sources, so sources that have a finite extent in phase space.
Okay.
We do have some first results there. Yeah.
Okay. Thank you. I also see a question of Andreas. What about arbitrary wavefronts as generated by interconnection with a prior surface?
So as I said, this is all geometrical optics currently. We are working on incorporating phase information and wave characteristics, but that's not in the current model yet.
Okay. Are you able to put in some manufacturing constraints? So you calculate the surfaces and we saw that depending on the configuration, you use different models or it's possible to extend it. Can you put in the boundary conditions some constraints for the manufacturing of these surfaces?
We currently not. So we find a freeform surface. Basically, we compute it on a grid, right? So we get a point cloud that describes a reflector or lens surface. But indeed, we are also working on trying, for instance, to minimize size or to minimize volume, these types of constraints. And we're a design group. We don't manufacture stuff ourselves, but we do work together with other universities who make and measure optical systems. So that's work in progress. Yeah.
Yes. So actually the models that you have now can be seen as ideal starting points where you later on can add a real source and can have a final optimization run in, for example, the non-sequential mode, and then you optimize, you fine-tune it, and then you have a finished design.
That's one of the options, yeah, but we do also like to include real sources. So we are working on having more realistic sources in our models too. Yeah.
Okay. Thank you. I see some other questions as well. Can wave optics model being, a question is if the wave optics modeling can be integrated here.
We are aiming to do that. So currently, one of the ideas we have is to treat everything with geometrical optics up until the last optical surface, and then do wave optics from the last optical surface to the target that you're trying to reach. That's the first step that we're currently working on.
Okay. The next question is from Haken. He's asking or saying, I love the idea of using this chicken and egg concept for phase retrieval. Can you tell us a bit more about this? Have you tried implementing it in an optical system?
So we didn't make an optical system yet, but we do have ray trace results, and we have published on the chicken egg example. So that is currently working there. There we are also working on a different description. So we use these two targets for phase retrieval. You can also use two sources, that sounds a bit strange, but two planes basically to specify a source. And what is interesting, if you have a description of the source by two planes and of the target by two planes, then you can put them together, right? You can glue them together like Lego bricks. You can concatenate optical systems. So that is also something that we are currently looking at.
Okay, thank you. I believe that's the question of Thierry Lepine. He asked if you did some experimental validation measurements, but I believe, yeah, you just indicated that you were doing simulations. So I go to the question of Julius. Julius says, you showed no crossover and double crossover, intermediate quasi-focus. What happens when there is only one decrossover, which would generate quasi-cylindrical freeform surfaces?
I didn't quite get that. Can you say again?
Yes, so basically,
Julius.
Julius, please.
I can speak. Okay. So the idea is that you have light coming in from a refractor, and if that refractor is more or less planar, then you have a wavefront coming back, which is then doing whatever it's doing. You also showed something where you would have like a concave or nearly spherical shape, where you have like something like an intermediate quasi-focus, right?
Yeah.
And my question is, isn't it like you showed the maximum thing in one of your first slides, two maximum numbers to make it convex? Huh? So it seems to me that if you make one a minimum, then you would have a solution where in this direction it would still go like that, but in the other direction, or in this direction, it would go as before. But in the other direction, you would have the crossover that you would get from a cylindrical reflector. And what happens to the math when you try to achieve that?
The problem is, if you're solving the equation in 3D, you either want a concave or a convex surface, which means that in the equation, I always show you have a plus or a minus sign. You want to choose the plus sign because that leads to concave, convex surfaces. If you choose the minus sign in that equation, then you get saddle surfaces. So we're also looking into that, because if you want to have like periodic structures, and you want to have them not only continuous but also smooth, then you do not only need convex concave, but you also need these saddle surfaces to glue them together.
Right. Okay.
Okay. Thank you, Martijn. With this, I would like to thank you again for the presentation and for your answers to the questions.